Hello, everybody. We're just going to check the restreamer's working here. Uh, Good evening, everyone. Welcome to our last unit, not our last video, but our last new unit of AP Physics 1 review. We're going to be taking a look at torque and rotational motion. And really quickly, before we get started, I am just going to really quickly check the audio levels on my phone just to make sure we don't have any weird artifacts with the microphone. Haven't had any show up on these past few recordings, but if it happens, it's really annoying and it's really hard for me to tell if I don't check early, so I want to make sure that it sounds good. Alright, that looks cool. Alrighty. Um, so, um, Yeah, as usual, so what we're going to do is we're going to begin by looking through some of the ideas generally. And this is one unit where that actually is going to really be beneficial because there's a lot of new Greek letters, a lot of new kind of concepts, and it's difficult to think about how they relate to. Um, they might be a little esoteric to begin with, but once we kind of get a kind of a handle of what they're actually representing, that we'll find that they actually make things much easier to use. Then once we go through that, we'll take a look at some practice AP multiple choice questions and some practice FRQs, just to go over all the different variations we have here. As usual, we have chat windows up on the left from both YouTube and Twitch. If you see me looking over this way, that's just me double checking to make sure, well, that everything on the stream is going all right, but then to see if you guys have any questions. And if you have any questions, please type them in the chat. Let me know, and I can go back over something if it's a little bit confusing still. Yeah, hopefully we'll be able to make torque and rotational motion something that you'll just have down. Cool. So let's begin with a circle. So, oh, I thought that was gonna be hollow, but that's okay. So we'll have some circle with some radius. And so this has a radius, we'll call it R. Just keep things symbolic. And so we want to think about if we were to start to rotate this circle, we can think about some point on the end of the circle being pulled around the edge. It's kind of moving around, and so let's say we rotate it by some angle theta. And so this angle is going to be enclosed, or going to enclose the two different places that we move between. We can think of this very similarly to a change in position. And so our first task will be to find a way to relate this angle theta to what we call the arc length, which is going to be this section bound by either side, by either radius inside this angle theta. And so what we can do is we can think of these in terms of fractions. So if we think of this, this theta as just kind of taking some fraction of the circle, it's just taking some piece of the pie, it's going to take a fraction proportional to its angle, which is just theta in radians, divided by the total amount, the whole pie, the whole pizza. The total amount, the complete circle in radians is 2 pi. And so we expect this fraction to be the equivalent fraction, it's the equivalent ratio of our arc length, this s, and our total distance around the edge of the circle, which is going to be our circumference. So we can say this is our s over our circumference, which we define as 2 pi r. And so now we can multiply both sides by 2 pi, cancel these out here, giving us that theta is equal to our s, the linear term, the arc length, divided by the radius r. But now, so we're thinking about this point moving around the edge, and we think as it's moving, we want to know how quickly it's traveling, right? Is it going around at a slow rate, or is it zipping around in an untidy circle that I realize I'm not very good at drawing perfect circles? That's okay. That's why we have computer tools to help me draw this circle. And so that kind of a quantity is going to depend on the radius, because we can think of this point as tracing out our circumference, and our circumference depends on the radius of the circle. So we can think of this velocity as traveling a distance per time, and so the total distance we travel would be a full circumference, so that is 2 pi r, and the time it takes us to travel that is going to be our period, which, just like we had in simple harmonic motion, and we saw this a little earlier in centripetal motion, is going to be our capital T here. And so we have this, so this depends on our radius, though. This doesn't tell us the rate of change at which the angle is opening. We want to think of a way that, that theta changes with time, in a way that the angle's kind of opening up. And so this is going to be invariant of the radius. And so all we do is we just divide out the radius. We have, for an angular momentum, we travel 2 pi radians when we complete a full lap. And the time it takes us to complete a full lap, again, is that same t. So we get this omega is equal to the same thing as our velocity up here, only now we divide it by r again. And so we're starting to see a little bit of a pattern here, right? We have a new angular term, and so these are going to be in a Greek letter, and they're equivalent to a linear term. So that would be like our position, our arc length, or our velocity. And these are related by dividing out the radius. And we'll see this idea persist when we move to acceleration. So for acceleration, an angular acceleration, alpha, is just going to equal our a, which is our tangential acceleration, not our centripetal acceleration, not the radially inwards, but this is pointing along the edge. So this would imply an increased rate of rotation. We're either speeding up the rate of rotation or slowing down the rate of rotation, divided by the radius again. And so what's nice about this set now, so now we have three variables, three different kind of angular quantities we can use. And what's very nice about these is because they are directly related to our linear components, that means we can use all of our linear kinematic equations on them. So similarly to how we had, let's say, Vf minus Vi over t was equal to our acceleration. Well, now we can take this same equation and plug it in with our angular terms. We have, instead of v, it's an omega. We have omega f minus omega I, still divided by our time. Our time is going to be the same throughout. It's going to equal, instead of a, it's going to equal an alpha. And so we can do this for any of the kinematics we have. I'm not going to go through all of them. But yeah, anytime you would see an x, you can replace it with a theta. Anytime you would see a v, you replace it with an omega. And anytime you see an a, you replace it with an alpha. Now, to continue on this, this sort of corollary journey, we're looking to correlate our linear quantities to our angular quantities. We want to think about next force. And so we've talked about forces in the past, specifically like centripetal forces when we're dealing with rotation. But the centripetal forces would accelerate us inwards. If we want to induce a rotation, to actually get something to begin to twist, that's going to be what we call a torque. And so a torque, we use a tau, and then we can use what's called a cross product. Now we'll go into the cross product a little bit more in depth some other time, but for all we really need to know is we expect this to be a perpendicular. We can use this as the magnitude of both of these multiplied together. So this would be the magnitude of the radius times the magnitude of the force times the sine of the angle between them. And so we're going to be looking for cases where we want these to be 90 degrees. That maximizes our torque because the sine of 90 degrees goes to 1. Similarly, we can see that the sine of 0 goes to 0, meaning if there's no angle between these, if the force is pointing on the same direction as the radius, this doesn't induce a torque, and this gives us a torque value of 0. And then we'll deal with positive and negative dealing with directions like we usually do, but instead of right and left, we'd rather think about these as clockwise or counterclockwise. And it's going to be the same sort of thing that we saw before, where we define our coordinates to have one of these directions be positive, and then if something is moving in the opposite direction, we give that a negative sign. Cool, cool. And so, following along from this then, if torque is our radial equivalent to force, we can now get a radial equivalent of Newton's second law. So, Newton's second law, as a quick reminder, was our net force is going to equal our mass times our acceleration. And so the equivalent statement in the angular sense would be that our net torque is going to equal our moment of inertia instead of our mass. Although we'll unpack this a little bit after, and we'll see that this is going to play a similar role to mass, times our angular acceleration. This is our alpha. And so we can then also use equilibrium problems, meaning that we expect for a balanced system this alpha to go to 0, and so that means our net torque is going to sum to 0, just like we did equilibrium problems in Newton's second law with the linear dynamics. Yeah, and so let's unpack this moment of inertia a little bit here. And so this quantity is basically it's the kind of allegory to mass, and I don't want to use an equal sign here because it's not the same thing, but it plays the same role that mass does in these types of equations, which is an inertial property. If we think about what mass does, let's take a look at this Newton's second law real quick. So we have our F equals ma, but then we can see if we rearrange this a little, our acceleration is equal to our force divided by our mass. And so we see as our mass gets really large, for the same amount of force, our acceleration gets very small. So we see the larger this mass is, the more it resists a change in its motion, is how we want to start thinking about this. We don't want to, if a mass is very light, that if there is not a lot of mass, then this is very easy to change how this object moves. We can accelerate it up to high speeds very quickly, and we can bring it to a stop fairly easily also. If we have a lot more mass, this is going to take more force to reach those same levels of acceleration. And so what the moment of inertia does is it's an object's inertia in a way to resist its motion, but now this is an object's resistance to a change in its rotation. So it's not only the mass, but we multiply it by the radius of this squared. And there's more to it than that, because based on what our objects are, we can add these linearly, which means that these often come from integration. And so for our purposes, these will usually either be provided for us, or you'll have a lookup table that you can look for the general shape that we're hoping for. And so, but for just mr squared, this would be a point-like particle. So if we just had a single mass floating around, like moving around a circle, not attached to anything, that would be this mr squared type behavior. Yeah, but and then another one, I guess that's the only one you vaguely want to memorize, but really you don't need to memorize any of them. They should be provided, but if you have them in the back of your head, it's going to make going through the multiple choice section a little bit quicker. And so I guess this is the only one I'd recommend memorizing. The other one that kind of stuck with me was for a disk or a cylinder, it is 1/2 mr squared. Because we deal with a lot of rolling disks. That's another popular object. So let's see. We've got our allegory for mass, our allegory for force, and then all of our kinematic variables. Um, we just have two more. That's going to be an allegory for momentum. And so we can think about how we previously defined momentum as a mass times velocity. This is now going to go to an angular momentum, which we define with an L. And instead of mass, we're going to plug in that moment of inertia. And instead of velocity, we're going to plug in that omega. So we're just kind of translating point for point over here. And so this is going to be a property that's conserved even if we change our moment of inertia, our I, as maybe masses shift relative to the radius. I guess one more thing I do want to bring up on the I. Generally speaking, the I is going to be higher if we have more mass distributed further away from the radius. So if we have masses of, if we have two objects of equal mass and equal radius, but one of them is, say, like a hoop, it's got its mass kind of all pulled out to the side, and the other one is just a uniform disk, we expect the hoop to have a higher moment of inertia. Without having to do any calculations on that, we can just assume, well, that's going to be a greater value because that's the mass is generally further away from our axis of rotation. Yeah, and so let's see. So that's for our angular momentum. I guess we can also mention our angular momentum we can compare to a linear momentum similarly to how we did with torque. So if we are dealing with a linear collision, hitting an object and then starting it to rotate, we can do R cross P, which again is going to be the magnitudes of both times the sign between them, giving us our maximum when these hit each other at the perpendicular. And then for our last piece, is this going to fit on the screen? I think we will. Is going to be our kinetic energy. And so before we saw kinetic energy was, oops, let's get a little bit more space for that, was equal to 1/2 mv squared. And so if we directly translate that point for point, our rotational kinetic energy is equal to 1/2, instead of m, we'll use our I. And instead of v, we'll use our omega. We'll have omega squared. 1/2 omega squared is our rotational kinetic energy. Now bear in mind, it's important to note that this does not account for an object that is still moving in a translational manner. So we can have objects that are rolling, and so they'll be moving their center of mass while also having rotational kinetic energy. And in that case, we have to sum them both together. So we'll say, to express this mathematically, our total kinetic energy is equal to the rotational piece plus the translational piece, which would be just that linear version we had, the 1/2 mv squared. Good. And so a lot of definitions just right off the bat. A lot of little equations and lots of stuff. It's okay if this is confusing. There's just a lot of Greek letters all at once. But honestly, once you kind of get how these relate to the previous things we've done, you'll see that all of our previous relations that we've worked with will still apply. We'll still be able to use our conservation of energy equations just like before. We'll still be able to use all of our dynamics equations just like before. And we'll be able to use all of our kinematics like before. There's just going to be a few subtle twists here and there, and that's what we'll be looking at today. So yeah, I guess on that note, if we've got no questions, let's move on to some of the problems. So we're going to start with a uniform meter stick with mass 2 kilograms is pivoted at the 40 centimeter mark. Is that covered up? Oh, that is covered up. Okay, I can move this. Is that better? That's a little better. Yeah. Okay. I forgot we have our little wrong side. We have our stuff on the right, trying to put stuff on the screen, but it makes it sometimes it covers things up, which is a little bit annoying. But I'll try to be a bit more careful about that. So we've got our meter stick, and it's pivoted at the 40 centimeter mark, so not quite at the halfway point. and it has a mass of 2 kilograms. And so the fact that we are told it is uniform means that we expect this to be acting as a force at its center of mass, and the center of mass we expect to be at the halfway point. And so that is a force of gravity, mg, for a mass of 0.2 kilograms. Where should one hang a mass of 0.5 kilograms to balance the stick? Well, so we already know it's going to be on the left, so we expect it to be something less than 40 centimeters. So we can rule out C and D here, but to actually calculate this, we want to use a balance in torques. To balance the stick, that means we expect our angular acceleration to go to 0. So this tells us then that our net torques have to also equal 0. And if we look at our two torques we first have the force of gravity due to the stick trying to rotate us in the clockwise direction. Let's call that positive. And so that's just going to be our mg. I guess we'll call that m1. And then m2, so we'll have this be mass 1, and this will be mass 2. And so our mg is going to be inducing a torque. I was struggling to find the word there. At a radius from this pivot point of 10 centimeters. And so I get 10 centimeters from the halfway point being at 50 centimeters and our pivot point being at 40 centimeters. So 50 minus 40 gives us 10. And so our force would be 0.2 times, we'll just use 10 for G. Well, in fact, actually, we can just use G for G because G is going to cancel out. Times, we'll give that a positive 0.1 meters. Actually, we can do this with centimeters. Doesn't really matter. Usually we'll want to use meters because then that plays nicely with other units, but we're looking for an answer in centimeters, so us using centimeters here isn't going to really be a problem. And then our other force, we expect this is going to be where we're going to hang the next mass. And so we know it's going to be on the left, so we'll give it a negative sign. Because we also expect this to induce a rotation in the clockwise direction. No, sorry, in the counterclockwise direction. And so that we have a mass of 0.5 being accelerated at g, and that's going to be at some distance r from the pivot point, from our fulcrum, if you like. And we expect this to all equal 0. So we can add this to both sides. We'll cancel out our g, and that gives us 0.2 times 10 centimeters is equal to 0.5 times our distance r. And this is our distance away from the center point that we should hang this mass. So we'll divide both sides by 0.5, which is the same as multiplying by 2. And then we have, that ends up giving us a distance of 4 centimeters is equal to r. 0.5 divided by 0.5 is multiplying by 2. 0.2 times 10 is 2 centimeters. 2 times 2 is 4 centimeters. Is kind of the thought process I used there. Again, you'll have a calculator for this too, so if you're not quick with mental math, you can always just type stuff in. There's no shame in that. And so we expect this to be 4 centimeters to the left of our pivot point. And so we know our pivot point is at the 40 centimeter mark. So that means we're going to hang this at the 36 centimeter mark. So option B is going to be our best choice there. For number 2, we've got a uniform meter stick is balanced at its midpoint with several forces applied as shown below. If the stick is in equilibrium, the magnitude of force X in newtons is going to be equal to which? Okay, so this is the same type of thing as we have before, only now instead of masses, we're just given the forces directly. And so we expect our net torques to equal 0, but in this case, we have, let's define clockwise as positive again. And so we have a positive 20 newtons, positive 200 newtons at 40 centimeters. And then we have, also in the clockwise direction, that's the positive force X, X at a 20 centimeters. And then we have a negative because the only force trying to rotate us to the left is this 300 newtons, and that's trying to rotate us in the counterclockwise direction, and that is being applied 30 centimeters from our fulcrum. So this is all going to equal 0, so we can bring this over to the other side. I'm actually going to pull this kind of down here, and we'll start writing underneath this guy here. Yeah, that should work. And so we get, let's see, so we have 300 times 30. And then we'll bring this 200 newtons over also, minus 200 newtons times 40 centimeters is going to equal our x times 20 centimeters. And so to get x on its own, we'll divide both sides by 20, giving us x is equal to 300 newtons times 30 centimeters minus 200 newtons times 40 centimeters, all divided by 20 centimeters. And so the units of centimeters cancel out here, so it actually doesn't matter that we didn't convert this into meters. But that being said, we will want to convert to meters if we are then going to use a kinematic, if we are going to use this alpha to plug into some sort of rotation. But the fact that this is all balanced means that we don't need to worry about this too much. And so we have, that's going to be 9,000 minus 8,000 divided by 20. So that's 1,000 divided by 20, which is 500 divided by 10, which is 50. So A is going to be our best choice here. Yeah, again, feel free to use a calculator. That will be an option on the actual AP test. So 3 is more of a conceptual one. We want to see, we're given 4 sets of, or 4 different door handles, or door hinges, I guess. And we want to rotate them around. We can see we have these little, this point is going to be our fulcrum here. And we want to be able to swing the door, I guess we'll swing it open that way. And so we want to know which one of these forces is going to give us the largest torque. Now, A is not going to be a good choice because this is being applied right at the axis of rotation. So we can think of, again, we think of our torque is going to be the radius times the force times the sine of the angle between them. And this one, the radius, goes to 0 because our radial distance from the axis of rotation is 0 there. So A is not a good choice here. B is acting further out, which is good, but we're applying this at an angle. So we see this angle theta is going to be less than 90 degrees, and so therefore our sine of theta is going to be less than 1. So this puts us at less torque. Also, the same argument with D. If we look at this as now our angle of theta. Sorry, not that one. That's not going to be our angle theta. We want the angle between the radius and the thing. So this would be our angle theta. Either way, though, it's still less than 90 degrees. So we expect C to be our best choice because this maximizes our sine term. That makes our sine just go to 1, which is the maximum sine can be. And this is at our maximum radius because it's all the way at the end, and it's the same magnitude as force as every other one. Good, good. Number 4, we've got a meter stick. A meter stick is supported at each side by a spring scale. A heavy mass is then hung on the meter stick so that the spring scale on the left side, or the left-hand side, reads 4 times the value of the spring scale on the right-hand side. If the mass of the meter stick is negligible compared to the hanging mass, how far from the right-hand side is the large mass hanging? So what we've got here, I'm actually going to really quickly get us a new page just because I kind of want to draw this one out here. There we go. So we've got a meter stick hanging from 2 springs on either side. And so these springs are measuring the force that is being pulled down because they are pulling upwards with equal and opposite force. And so based on the distribution of where the force is at, tells us kind of where we expect our mass to be hanging. And let me double check again. They said the condition we want to satisfy is that the left-hand side reads 4 times the value than that of the right-hand side. So we expect our mass to be hanging towards the left. And so, yeah, so let's see. We want to take this as the force up this way. So this is still going to reach an equilibrium, right? And so we know there's going to be a force down here. We expect it to be on this side of our axis of rotation. If this x is going to be our axis of rotation, this is where we're hanging the mass. And so we expect, I guess we'll call this the force of the left spring. We'll call that FL. And this is the force of the right spring, FR. We want the condition that FL is equal to 4FR. Okay, yep. Just wanted to make sure I didn't get that the wrong way around. I would feel really silly otherwise. And so we want to find the conditions such that this would be the case. And so that then means we have to have our net torque go to 0 if this is all going to be balanced. And we have, let's see. So we'll have a positive, I guess let's call FR positive. So that's going to be moving in the counterclockwise direction this time. We chose that to be positive because that also means that our mass term will also be positive. And so we have a positive FR times the distance is L over 2. That's our radius. Oh, that's not a 2. I was going to write L over R there. That's not what we're looking for. And then we have an FL also acting at a distance of L over 2. This is also just coming from length of the meter stick, and then we divide it by 2 to just get the halfway points. The fulcrum is at the halfway point, and so then this tells us the radial distance from the axis of rotation that these forces are acting on is at a distance of L over 2. And then we have one more mass, and that's going to be a positive one, because we said it's going to try to rotate us in the counterclockwise direction, and we defined that as positive. And that's going to be our mg, and that's acting at some distance r. And the r is what we want to look for. And so this has to equal 0. Let's see. And so let's combine these terms. FL is equal to 4R. So we'll have FR times L over 2 minus, plugging in for FL, 4FR, again times L over 2. And now we can combine these terms. This is, we still have the plus MGR. We don't lose that term. But yeah, and now we have, we can combine these. So we have a negative 3FR minus L over 2, or sorry, times L over 2, plus our MGR is equal to 0. We can bring that over to the other side, giving us our MGR is equal to 3FR times our L over 2 distance. And let's see, are we given any... we're not given any conditions on the mass, unfortunately. If the mass of the meter stick is negligible compared to the hanging mass. Okay. Yeah, and so that tells us, because we unfortunately don't know FR. Oh, but we do know 5FR is equal. So if the mass of the meter stick is negligible compared to the hanging mass, that tells us by Newton's third law, by Newton's second law, again, because this isn't accelerating in the translational direction, our total downwards acceleration, our total downwards force is going to equal our total upwards forces, which is going to be Fr plus Fl, which I'll plug in as 4Fr. So our mg is really equal to 5Fr. So now we can plug this in and cancel our Frs out. So we get 5 times our force on the right times our radius r that we want to hang the mass from is equal to 3Fr times L over 2. We'll divide both sides by Fr, and then we'll divide both sides by 5 to get our radius is equal to 3/5 of half of our length. So that tells us our half of our length, this was a meter stick, so this is 50 centimeters, and 3/5 of 50 centimeters is 30 centimeters. So we hang this mass 30 centimeters away from the fulcrum, so away from the center, or 20 centimeters, this is really not to scale now that I look at it, 20 centimeters away from the left edge. So from the left edge is 20 centimeters, so we're asked how far do we hang it from the right side. Well, that's going to be 100 centimeters minus 20, because the right side is 100 centimeters away from the left side, and that is going to be 80 centimeters. So option D. Good, good. Any questions on how we did that? That was actually kind of a tricky one. Nope, looks good. Cool, cool. All right, next we've got a uniform meter stick, has a 45-gram mass played at the 20 centimeter mark as shown in the picture in the figure. If a pivot is placed at the 42.5 centimeter mark, and the meter stick remains horizontal in static equilibrium, what is the mass of the meter stick? So we expect the meter stick to, again, if it's uniform, to be inducing a force at the 50 centimeter mark. So this is at a distance of 7.5 centimeters away from the fulcrum, and this was inducing a force of m times g. We can compare that to, we expect that to be an equal torque. Again, so shorthand methods, we usually are working with, we want to set our net torques equal to 0, right? But we can kind of skip ahead to say if there's only two, that means the one rotating rotating in the clockwise direction has to equal the one rotating in the counterclockwise direction. And so that tells us that mg times 7.5 centimeters is going to equal our our known mass, which is 45 grams times g again. And this is acting, it's at the 20 centimeter mark from 42.5, so this is 22.5 centimeters from our fulcrum. We can divide both sides by g, and we want to get m on its own. And this might be one that I actually need a calculator for, because we've got 45 times 22.5 divided by 7.5. And I kind of ran out of space at the bottom there, but that's okay. And so yeah, I am going to use a calculator. Just plugging these in real quick gives us a mass of 135 grams, which is going to be option D. Cool. Any questions on how we did that? Oh, hello, Evbotica. I like the little the lizard. Is that a lizard? Gecko monitor? Well, I like that you're monitoring the stream. I appreciate that. We just finished our first round of multiple choice practice, and now oh, that was our scratch work from one of those. We're going to take a look at the next round. So we've got a massless rigid rod of length 3d is pivoted at a fixed point W, right up here. And two forces, each of magnitude F, are applied vertically upwards as shown. A third vertical force of magnitude F may be applied either upwards or downwards at one of the labeled points. With a proper choice of direction at each point, the rod can be in equilibrium if the third force is placed where? Okay, so so we want this to reach equilibrium, and so we have let's see how much we're off equilibrium by, and so that's going to be finding our net torque. And so that's going to be, with just these two forces, we have rotating us clockwise. Let's just define clockwise as positive in this case. We have a force of a torque of F times D. And then in the counterclockwise direction, which we'll define as negative, we have a force of F, or a torque of F times 2D. So our net torque is a negative FD. So what we can do is we can just add a positive FD. So that's going to be a force to induce a torque in the clockwise direction at a distance d away. Now this could be at v if we applied it upwards, or it could be at x if we applied it downwards. Does it have any conditions on where we can apply it? Applied either upwards or downwards, so it can be either. So our option B is going to be our best choice there. V or X. Komodo Dragon, very nice. Komodo hype, I like it. Komodo is a type of monitor. They're vicious beasts. It's quite exciting, really. You can see some cool, yeah. There's some very cool nature documentaries out there, but I don't want to go on a whole tangent on that. Otherwise, we'll never get through this. Yeah, and so we've got, next we have a man on a 5-meter plank of uniform plank of mass 100 kilograms. So we expect that to be giving us a force down here. At the top of a building with 2 meters extended over the edge. So that means we can treat this point as a fulcrum. How far can a 50-kilogram person venture past the edge of the building on the plank before the plank just begins to tip? Now this, we can actually use a shortcut here, because his mass is half of the mass of the. Okay, let me half of the mass of the plank. Basically, what this is, so we can treat this first torque is the mass of the plank times g at some distance r away. In fact, we know this r, right? Because this is at the 2-meter mark, and this is 5 meters long. So that's going to be, and we expect this to be at 2.5. So this is going to be 0.5 meters radius, which I can't really fit down there. It's close enough. Close enough. But our person is also going to be, he's going to be inducing a torque on the opposite side. But his mass is half of that. We can treat this as the mass of the plank over 2 times g. And so for these to be equal, we want mpg over 0.5 meters is going to equal to, we'll have mp over 2 times g times some distance r. And so the shortcut would be we cancel these out, and we expect our r to be double that, right? We can just say as our mass is doubled for the first torque, for a mass of half that magnitude to induce the same amount of torque, it has to be twice as far away. And so that's what we get here when we multiply that 2. We have 2 times 0.5 meters is equal to our r. 2 times 0.5 is just 1. And so that's going to be option B here. Cool, cool. Any questions on that? Looks good. All right. To weigh a fish, a person hangs a tackle box of mass 3.5 kilograms and a cooler of mass 5 kilograms. I like that they included what these masses were. It's like it's a tackle box and a cooler. So that's what you'd have while fishing. That's kind of nice. And ends at the ends of a uniform rigid pole that is suspended by a rope attached to its center. The system bounces when the fish hangs at a point 1/4 of the length from the tackle box. What is the mass of the fish? So let's define, in this case, moving counterclockwise as positive. And so our counterclockwise torques are going to equal our clockwise torques. And so that is a 3.5 kilograms times g. These are all going to be multiplied by g, so we'll be able to cancel that out, but we'll include it for now. And that's at a distance from the fulcrum of L over 2. They like the curly L. I'll use the curly L. That's fine. And then also in the counterclockwise direction, we have the fish. We're just going to use as mass m because we don't know what it is. We want to solve for that. But we know it's at a distance L over 4. And we expect this to equal the clockwise torques, which is just one torque. This is just the 5 kilogram mass hanging downwards, either also being accelerated at acceleration g. And this is at a distance L over 2. So now we want to solve this for m. Let's start by canceling all of our g's. In fact, we can even cancel all of our l's, although we do still keep the fractions. And so let's bring this 3.5 over. Gives us m over 4 is equal to, we have 5 over 2 minus 3.5 over 2. And so that's 2.5 minus 1.75. That looks right. And that is going to be 0.75. Yeah, that looks right. Is that an option? That's not an option. Okay, I did that wrong. Maybe we do that with a calculator? How's that? No, that's okay. That's all good. Oh, no, but so this is 0.75, but this is still equal to m over 4. So we've got to multiply this by 4. And so that's then going to give us, oh, I shouldn't struggle with that, but that's 2 times, so that's 3. Yeah, it's 3/4. So yeah, this is 3/4 of a meter multiplied by 4 is sorry, 3/4 of a kilogram multiplied by 4 is 3 kilograms. Yeah, I'll just write out the step we took there. It's 0.75 times 4 is what we just did for that last step. Good. Any questions on how we did that? I got myself a little bit turned around there. That's okay. Yeah, one of the advantages of multiple choice is we can tell whenever we're right out because our option just doesn't show up on the board. So for number 9, we've got 2 objects of masses 6 and 8 kilograms are hung from the ends of a stick that is 70 centimeters long and has marks every 10 centimeters as shown. Okay, so that's what these little hashes are. If the mass of the stick is negligible, so we're only looking at masses of the 6 kilogram, the 8 kilogram, where should we hang a cord so this remains horizontal? Which of the points indicated should a cord be attached if the stick is to remain horizontal when suspended from the cord? That's what I was trying to say, but I'll just say it the way they wrote it. So we don't expect this to be C because that's going to be in the center, and so that would be off balance. We want the case where I guess I'll write this up here where I accidentally scribbled there. Where we want our 6 kilograms times its radius away, we'll call that R1. It's going to equal our 8 kilograms times its radius away, R2. Now notice how both of these were meant to be forces, so they would both have a G in there, but I kind of implicitly canceled that out. And so we can look at, I think we just want the ratio of R1 over R2, I suppose. How do we want to do that? Yeah, okay, so let's divide both sides. So R1 over R2, if we divide both sides by R2, gives us, then we have 6 kilograms over here, and then we divide the 6 kilograms over, so we have 8 over 6. So we want this to be like a 4 over 3 ratio, a 4 to 3 ratio, I guess. And so that's going to be option D, because this then gives the 6 kilogram 4 kind of hashes here. So 4 10-centimeter hashes, that's 40 centimeters. And this gives the 8 kilogram one 30 centimeters, hitting that ratio that we wanted to satisfy of 4 to 3, and one of the options that this is given. So D is going to be our best choice. Also, E doesn't even show up there, so that kind of lets us rule out E there, just because it's not on there. Cool. And so I think now we're still going to do a couple multiple choices, but these are going to focus a bit more on the rotational dynamics. From the older, so these are old AP questions. Some of them are older than others. And this used to be taught with these being very separate units. Torque would be taught very early in the year, in fact, before centripetal motion, and then rotational dynamics would be towards the end. It's kind of strange that they taught them that far apart. Excuse me. And so now they're taught together, which I think makes much more sense. But that does mean that we have to, that some of the problems are a little differentiated, and so we have to worry about that. Excuse me. There we go. So now we'll be looking at, we've got a uniform stick that has length L. The moment of inertia about the center of the stick on its own is just some I naught. A particle of mass m is attached to one end of the stick. The moment of inertia is going to be which? So we've got like a stick here. It's rotating around the center, and its moment of inertia about the center is I naught. And we can add moments of inertia linearly. That's what we discussed earlier. Did we mention that earlier? I think we mentioned that earlier. You can add up moments of inertia. If we have multiple things rotating, we can just say it's the moment of inertia of the stick plus the moment of inertia of the mass on the end. You just add them together. And then the mass on the end is going to have a moment of inertia of mr squared, but our r is L over 2. So that's going to be I naught plus m L over 2 squared. When we square this 1/2, it turns into a quarter. So that actually gives us A is our best choice here. This is kind of a tricky one. I bet a lot of people will go for B. B is a very appealing choice because it's half of ml squared, but you include the half under the square, so it scales down. Yeah, not that one's not obvious. It's okay if you guys missed that one. Next, we've got a light rigid rod with masses attached to its end is pivoted about a horizontal axis as shown above. When released from rest in the horizontal orientation, the rod begins to rotate with an angular acceleration of magnitude what? So this is going to be a torque problem, but now it's not in equilibrium. We expect this net torque to induce an angular acceleration. So to solve for this, that's then just going to be our alpha is equal to our net torque over our moment of inertia. I think the fact that they say it's a light rod, and they don't give us a mass of the rod, so I think that we just treat these as 2 point-like particles. So starting with our moment of inertia, we have a 3m L squared plus m plus a 2l squared. So this is going to give us 7ml squared on the bottom. But let's take a look at our net torques on the top first before we simplify. And that's going to be, we have a 3, so I guess let's say, I guess it doesn't say the direction we want. Yeah, let's say clockwise is positive. So, so it's actually going to be, so this is actually going to be a negative sign on the top here. We'll have a negative mass of 3m over times g, and that's operating at a length L away from the radius, so away from the pivot point. And then we have a positive m is trying to rotate us in the clockwise direction, and that's operating, again, accelerating at a rate g, and that's operating at a radius of 2L from our pivot point. So combining these, we have on the top, we have a negative mgl, so we have 2 mgl minus 3 mgl over 7 ml squared. M's cancel out. One of the L's cancels out. We have negative g over 7L. And they want the magnitude, so they don't care about the negative. I guess that tells us then, because we defined counterclockwise as negative, this is going to be in the counterclockwise direction. But it's at a magnitude of g over 7L. Good, good. Any questions on how we did that? Well, if you guys get lost, just feel free to type something in the chat, and I'll try to address the problems as they arise. But so far, we're doing pretty good, so that's exciting. Next we have, in which of the following diagrams is the torque about point O equal in magnitude to the torque about point X in the diagram above? Okay, so we have a force of magnitude F operating at a distance L away. So yeah, we want a magnitude of F times L. Oh, and so we can rule out A and B right away, because B is going to be the same case but with half the length, so nothing can really help that. And then A is pulling off to the side, so that's actually just going to be a torque of 0. And so this is then going to come down to a sine. And so we have, for C and D, we have twice the force, so we have a torque of magnitude 2F times L, but then each of them are times a sine term. We have sine of 30 and sine of 60. And so we want the sine of whichever gives us a factor of 1/2. And I don't know if it's 30 actually. I'm gonna double check. I should probably know this. Oh, it's good. No, it's gonna be 30. It's gonna be 30 because okay, fine. I will double check just to be safe because I have a calculator here. But I am, yep, it's 30. I was vaguely confident before, but it's worth double checking. Hey, how's it going? Welcome to chat here. And so we've got yeah, so that's going to be 0.5. 2 times 0.5 cancels out to be 1. And our torque is going to be equal to FL. So D is going to be our best choice here. Any questions on how we did that? Nope. All right. Looks good. Cool. Next we've got a mass of an ant of mass m is clinging to the rim of a flywheel with radius r, as shown above here. Flywheel rotates clockwise on a horizontal shaft with constant angular velocity omega. As the wheel rotates, the ant revolves past the stationary points 1, 2, 3, and 4. It's kind of moving around this way. And can adhere to the wheel with a force much greater than its own weight. So we want to know it will be most difficult for the ant to adhere to the wheel as it revolves past which of the 4 points. So this is kind of just centripetal motion, right? And so we expect that the centripetal force that the ant has to achieve, so the centripetal force of the ant is going to be, I guess we'll call this the adherence force, Fa. And then based on where we're at, we can choose whether or not we want to add or subtract. So we also need to factor in the gravity force for the ant. At 2 and 4, it's perpendicular, so the gravity force isn't going to affect it at all. But at 1, it's in the same direction as the adherence force, so it's going to help it out, meaning that the ant is only going to have to hold on for the centripetal force, which is mv squared over r, minus our force of gravity. But then in the case, so that's for number 1. But for number 3, the centripetal force is the adhesive force minus gravity, because gravity is now pointing in the opposite direction, meaning that the adhesive force that the ant must reach is the same centripetal force, but now it also is adding up his own weight onto that. So that means that he's going to have to use a much stronger force at 3, therefore it will be the most difficult point for it to hang on. So point 3 is going to be our challenging point. And 5, actually, we kind of did 5 on its own here. What is the magnitude of the adhesion force to stay on at point 3? Well, that's just going to be this Fc plus Fg. And in this case, we had that as mv squared over r plus mg. And they would like this in terms of the omega. And so remember, our omega is v over r. So the v squared gives us, v is equal to omega times r. And we plug in that here. So we have m omega r squared over r plus mg, which is equal to m omega squared times r plus mg, which is going to be option D. There we go. Any questions on how we translated between velocity, like the mv squared over r, to the angular velocity, omega? This is a good activity to practice at home to make sure if you're still familiar with how we move between these, is double check this relationship for yourself to make sure we expect mv squared over r to equal m omega squared times r. Feel free to pencil through that if you want to prove it for yourself. I think that's a nice activity to solidify these relations. Cool. So I think this is our last multiple choice, and then we're going to move on to a couple FRQs. We've got a turntable that is initially at rest, is set in motion with a constant angular acceleration alpha. What is the velocity of the turntable after it has made one complete revolution? So what we can do, we can use our kinematics equations in the context of rotation. So if we were to have a constant acceleration and then be asked what is our velocity after a certain distance, we would want to use vf squared is equal to vi squared plus 2ad. Now in this case, well, for both cases, we're starting at 0, but we now want to substitute each of these linear terms for an angular term, giving us that our omega final, which is what we're looking for, omega final squared, excuse me, is going to equal 2 times our alpha times our distance that we've traveled. And so that's our theta, but we know for one complete revolution that theta has to equal 2 pi. And so to get omega on its own, we just take the square root, and that's going to be 2 alpha times 2 pi, or root 4 pi alpha, which is C. Cool, cool. Any questions on how we did that? No? Well, looks pretty good. You guys are great listeners. 7 and 8. Wow. Okay. So we're told for 7 and 8 to use these, but these are labeled as 11 and 12. Okay. Yeah. Consistency. That's what I like about College Board and AP. They are just consistent with their... yeah. Anyway, so we've got a wheel of rotational inertia I is mounted on a fixed frictionless axle. The angular speed omega of the wheel is increased from 0 to omega f, omega final, in a time interval t. What is the average net torque on the wheel during this time interval? So we expect the net torque to equal I times alpha, and then we can find the average alpha is just going to equal, so to set this equal to the same thing, we'll pull the I out front still, but our alpha is going to equal our final velocity minus our initial velocity over the time it took us to get there. And our initial velocity was 0. So this is just I omega f over t, which is D. Cool, cool. 12 now asks us, what is the average power input to the wheel during this time? Okay, so power, I wasn't expecting to see power here, but that's fine. Power, we expect to be work over time. And work, in a rotational sense, we usually treat work as force times distance. For an angular sense, we can treat it as torque times theta, the angle that we covered. And so we have our torque up here. So let's see. So we expect this P to still equal this I omega f over t times theta over t again. So we can combine those t's on the bottom. I omega f theta over t squared. And then this theta, we can think of this like a position, right? Or a distance. And our distance we travel is equal to our velocity times time. Our theta, oh, that looks kind of weird that close. Let's get a new line for it, like out here. Theta is going to equal our angular velocity times time. And so, do we have... So the only thing I'm not thrilled with... Oh, yeah, but that's where the 2 comes in. Okay. So I was a little confused because we aren't traveling at omega f the whole time. We're traveling at omega average. But that is just equal to omega final minus omega initial over 2. And that is 0. So it's omega final over 2. So plugging these all in, we get I omega final squared over, or times t over 2t squared. So we cancel out one of the t's. And so we have option B is our choice that we want. We have the I, we have the omega final squared, and then we have over 2t, but not t over 2t squared. We had a t squared, but it canceled out. Any questions on how we did that? All right, looks good, looks good. Let's keep on trucking. And I think this is our last multiple choice here. 2 blocks are joined by a light string that passes over the pulley as shown above, which has radius r and the moment of inertia I about its center. T1 and T2 are the tensions in the string on either side of the pulley, and alpha is the angular acceleration of the pulley. Which of the following equations best describes the pulley's rotational motion? So that's going to be... we have 2 forces of tension inducing a torque at a radius r. One of them is pulling us down this way, the other one's pulling us back this way. Down to the bottom, the other one's pulling us over to the left. And so if we're accelerating downwards, T2 is going to be the positive one. So we have a positive T2 times r minus a negative T1 times r is going to equal Ri times alpha. And we can factor out the r to give us option C is our best choice there. Cool. Any questions on these multiple choices? All right, well, until we get something to roll in, I'm just going to keep on going. We'll take a look at our FRQs here real quick. And so we're beginning with a cloth tape wound around a uniform cylinder that is then fastened to the ceiling and then left to roll down. Cylinder is held in tape with vertical and then released from rest, so it starts to roll. As it descends, it unwinds from the tape without slipping. And we are given the moment of inertia is 1/2 mr squared, which was the one we had in the beginning. So on the circle, we want to start by drawing all of our forces. And this one's going to be quite easy. There's only 2. We have a gravity force pulling us straight down. We'll call that Fg. And then we have a tension force, the tension in the tape, pulling us upwards. And that's applying on the left side here. So we can see that this has some radius to it. This is being applied at a radius. Our Fg is not. So now we want to find, in terms of g, find the downwards acceleration of the cylinder, the center of mass as it travels down. And so generally, we would find this with a Newton's second law. We would take our F net is equal to our mass times acceleration, and our net force, it's going to be our force of gravity. If we assume we're accelerating downwards, so we'll have downwards be the positive direction, minus our force of tension. It's equal to ma, and so that's mg minus ft equals ma. But then we get into a bit of a problem spot because we now have 2 unknowns. We don't know ft, we don't know our acceleration. But we can solve for ft using our angular acceleration. And so this tells us our torque induced is going to equal Ft times r. This is the only torque in the system. So this is the only thing that's going to induce a rotation. It's going to induce an angular rotation of, we still have our moment of inertia, times the angular acceleration alpha, which we know is equal to acceleration over r. And so we can divide, let's actually let's simplify this a little bit before we get it on its own. So because we want to get ft on its own here, right? And so we'll multiply both sides by divide both sides by r, excuse me. And so that gives us I is equal to a over r squared. And plugging in our I, that was 1/2 mr squared times a over r squared. R squareds cancel. Our ft is equal to 1/2 ma. And so now we can plug these in. I just realized now I haven't been using capital M's, even though they want us to be using a capital M. Again, not a big deal on the actual test, but it's worth staying consistent, I suppose. And so, yeah, so we can plug this in. And so we get mg minus our ft, which we just said was 1/2 ma, is equal to ma. Now we want to get both of our terms with acceleration together and then factor out our masses. Well, in fact, actually, we can divide our masses out. And so this gives us g is equal to, if we add 1/2 a to a, that is 3/2 a. Giving us our acceleration is 2/3 g. There we go. And that's in terms of g. That's what we're looking for. So very good. Next, we're asked, does the center of mass of the cylinder, so the center of the cylinder, move towards the left, towards the right, or straight down while it's descending? Now, when it's descending, we already noted all the forces we have acting on this. We have net forces pulling downwards and upwards. We have forces pulling downwards and upwards with a net force pulling downwards. We have no forces pulling us to the left or the right, so we actually don't expect any acceleration in the right or left direction. So we expect this to be moving straight down. So this is going straight down. I'm not going to write a full paragraph because, you know, this isn't a good format for that. But we'll just write because no horizontal forces. There we go. Good enough. Okay, next we've got, so this is going to be a bit more of a complicated FRQ. We've got a nice kind of complex system here. We've got a disc with a rod and a block to kind of form this rotating hammer type of a problem, which is attached to a string holding it up against a wall here. And we're given the various moments of inertia for each part. Well, we're given the moments of inertia for the disc and the rod, they're given their masses and lengths. And then we're given the mass of the block, which we know we'll just fill in. IB is going to be 2mr squared. That's going to be, is that a distance big R? Or is, so that, okay. No, let's be careful here then. So that's 2m times its added radius of 2r, because the length of the rod is 2r. So, that then goes to 4. This is a moment of inertia of 8mr squared. Is the moment of inertia of the block. We didn't actually need to solve that for that, but this is going to help us later on in the problem here. So first, we would like to determine the tension in the string, excuse me. And this is going to be due to balancing torques. We expect while this is an equilibrium, that our downwards force from the mass of the rod and the downwards force from the mass of the block to be canceled out by the rightwards force of tension in the string. And so this is an Ft acting at some radius r. This is some, we'll call this Fr. Do we want to call that Fr? Yeah, we'll call that Fgr. This is the force of gravity due to the rod. We'll call this FGB, force of gravity due to the block. Good. And so we expect our clockwise torques to cancel our counterclockwise torques. So our clockwise torque is just Ft operating at a radius r. And then our counterclockwise torques we have starting with Fgr is operating at a radius r, and then it is at some sine theta. See how we have this inner theta knot here? because this is going to be pointing straight downwards, that's a parallel line to this one. And by inside angle theorem, this inside angle there is going to be theta. So we have, this is then going to be the sine again. Sine of theta. And then also we have our FGB, force of gravity due to the block, acting at a radius of 2r, again at the sine theta. I guess they call us theta naught, don't they? Well, I'll use theta naught. That's fine. Good, good. And so we want to determine the tension in the spring. So we divide both sides by r. That actually gives us the tension on its own here. That being said, we do want this in terms of m and g. So let's get our forces of gravity nicely ordered up. And so we've got FGR is 1m. So that's just mg. Sorry, the mass of the rod is 1m. So FGR is just mg sine theta naught. And then the block is 2m. So we have 2mg times, we have then a 2 sine theta naught, because there was a 2r here. The r's got canceled, but the 2 didn't drop out. So that gives us our ft, when we combine these, 2 times 2 is 4, plus 1, gives us 5 mg sine of theta naught for our force of tension in the string. Good, good. Next we've got, next the string is now cut, and the disc rod block system is free to rotate. So instantly after the string is cut, we want to determine the magnitude of the angular acceleration of the disc, and then the magnitude of the linear acceleration of the mass at the end of the rod. So after the string is cut, we're just looking at these torques now. Only the torques that were pointing in the counterclockwise direction remain. And so we're going to be accelerating in the counterclockwise direction. So let's determine that as positive. And so we have then our net torque, which is still going to equal, it's going to equal this guy times r, because we just divided out the r, but it's the same thing here. So we have 5 mgr, just for a nice little shortcut here, times the sine of theta naught. This is the net torque in the counterclockwise direction, is going to equal our moment of inertia times our angular acceleration. Now, our moment of inertia is going to be a little tricky because it's all of these moments of inertia added together. And so to get our alpha on its own, we have to divide out our moment of inertia, which we have, so we still have our 5 mgr sine theta on top. But now we're dividing by the sum of, we've got 1.5 mr squared plus 4/3 mr squared. And do they want, no, they want little m's, don't they? Mr squared. And then we have our last one, which was 8 mr squared. See, that was the one we solved ourselves. So that did come in handy. And honestly, I kind of want to just leave it like that. We can simplify this for sure. We can combine these, and then we would see the masses would cancel. One of the radiuses would cancel. But we don't have to. It's in terms of m, r, theta, and g. So we can actually leave it like this. And I kind of want to do that just because... fine. We'll add them. So this is 8 times 1.5 is going to be 9.5, plus 4/3 is, that's 1.33. 9.5 plus 1.33 is going to be 10.833. So we have 5 mgr sine theta naught over 10.833 mr squared. Can cancel the m's, can cancel one of the r's, giving us 5g sine theta over 10.833 r. That's our alpha. That's our angular acceleration after this. And so now that we have our alpha, that makes part 2 very easy, because now we just want to find the linear acceleration of the mass at the end of the rod. And to move between linear acceleration and angular acceleration, we just multiply by r. And this is at a radius of 2r, so we'll multiply by an r on the top, multiply by 2. So we get 10, that's 5 times 2, g sine theta naught times an r over 10.833 r. And the r's cancel. Pretty simple. Good, good. Any questions on how we did that? Kind of moved through, used a few shortcuts there, so I moved through it a little quickly. Yeah, let me know if you guys have any trouble finding where these things came from. Yeah, and so then that gives us our A and our alpha. Good. And then C, as the disk rotates, the rod passes the horizontal position as shown above. We want to determine the linear speed of the mass at the end of the rod for the instant the rod is in the horizontal position. Okay, so let's actually get a new page, just because I don't think we're going to be able to fit this on this page. Okay, go on. There we go. Okay, we're looking good on time. So we wanted to know, once it passed this position, kind of at this horizontal, and to do that, we want to think about what we had before was a potential energy, and now it is being converted into a kinetic energy. Yeah, technically, yeah, you usually use these as not P, right? But it's a U. And so before, our initial case, we had the rod was contributing some potential energy because it had some mass that traveled down, and then the block itself also traveled down. And so these traveled a distance of, so the center of mass of the rod had an initial potential energy of, what did the rod weigh? The rod weighed 1m? Yep, okay. So that weighed mg, and then traveled a distance h, which is, we can relate to r and theta, because this is, that's theta, so that's going to be the cosine of theta, times r, that's 1 radius r, so that's going to be r cosine theta. And then we also have in our potential, a potential of the mass, which had 2m, again with multiplied by g, and that's acting at a distance of 2r, again going times the cosine of theta. So our initial energy of the system we can write as 5mgr cosine theta. Again, 2 times 2 is 4, plus 1 is 5. And this we can compare to our kinetic energy at the bottom. And so this is then going to equal our 1/2 I omega squared. And we want to know what our omega is. So to get omega on its own, we'll multiply by 2, divide by I, and take the square root. So we have 10, so omega is going to equal 10 mgr cosine theta, that's 5 times 2, divided by our I. What did we get for our I on its own? That was 10.833 mr squared. And then this is all under a square root. And so that gives, we can cancel out the m's, cancel out one of the r's. And so that then simplifies a little bit to 10g cosine theta over 10.833r. Now this isn't our final answer, because we wanted to know the linear speed of the mass. But this is the angular velocity that everything is rotating at. So to get the speed of the mass on its own, it's actually quite easy. We just convert this omega into a velocity. And velocity is equal to omega times r. And our radius in this case is 2r, is where the mass is out. So our velocity is equal to 2r times our omega, which is 10g cosine theta over 10.833 r. Cool. Any questions on how we did that? And yep, that was all we had for this FRQ. So let's take a look. This is going to be our last one. We've got a horizontal uniform rod, as shown above, has some length of 0.6 meters and a mass of 2 kilograms. The left end of the rod is attached to a vertical support up here, and the right end is supported by a spring. Supported by a cord that makes a 30-degree angle that's attached to a spring. The spring scale has negligible mass, but this measures the tension in the cord. We also are hanging a 0.5 kilogram block on the end. So we're rotating. This is our fulcrum. This is where we're rotating around, and we're inducing torques downwards, so in the clockwise direction, and then upwards in the counterclockwise direction with the spring. So yeah, let's start by drawing all of the forces acting on the rod. So we have the tension force pulling up this way. We have a force of gravity due to the block. We have a force of gravity due to the rod acting at the center. And then we have, I guess we'd call this a normal force from the hinge. And so that's going to be lifting us upwards. Now notice how we're going to be rotating from here. So this normal force does not induce any torque, but it prevents this from moving translationally downwards. We'll call this FGR. We'll call this FGM. FG, force of gravity due to the mass. That makes sense, I guess. And then this will be FT. And so now B wants us to find out what is going to be the reading on the spring scale. And so we expect this is an equilibrium, so we expect our torques to be balanced. So that tells us our counterclockwise torques, which is going to be Ft times the length of our rod, which is 0.6 meters, times our angle, or the sine of our angle, which is sine of 30 degrees. It's going to equal our counterclockwise torques. Now this is going to be our first mass, or our mass of the rod, which is 2 kilograms, times our acceleration due to gravity, times the radius that this is acting at, which is going to be half of our length, or 0.3 meters. And then we have an additional 0.5 kilograms, again accelerated due to gravity, acting at 0.6. Is that going to fit? Oh, it just doesn't fit. That's okay. We can kind of see it go off on the end there. And so we want to get Ft on its own. And so Ft, we just divide both sides by 0.6 and sine of 30 degrees. And so let's write this a little bit nicer. I'm going to pull the g out front here. We'll have 2 kilograms times 0.3 meters plus 0.5 kilograms times 0.6 meters. I'm going to need a calculator for this one, but that's okay. Divided by 0.6 meters times sine of 30 degrees. Okay, and then for G, we'll use, does it tell us to use 10? Then we're going to use 9.8 because I like 9.8 better. And if we're using a calculator already, then we might as well use it for a more accurate answer. Yeah, and so now I'm just going to plug in our values here. We have 9.8 times the quantity of 2 times 0.3 plus, again, make sure these are in parentheses, so we're multiplying before we're adding. Standard order of operations should do that, although my calculator is a little bit finicky. I'm using the one on my phone, and so sometimes it likes to abandon order of operations, which is not always the best case. But I get now, with careful use of my parentheses, force of tension is going to be 29.4 newtons, which is, again, just coming from our balancing torques. We expected our net torques to equal 0, was where that came from. And so now we want to calculate the magnitude of the force exerted by the hinge on the rod. And so this is then going to be a balancing a Newton's second law, not in the rotational sense. So we have the upwards component of our Ft plus our Fn. So we'd have the upwards component is going to be proportional to the sine of our angle times Ft. So if Ft times the sine of 30 degrees plus our Fn, which is what we want to solve for. We can maybe call this FH if you want it, for force of hinge. I don't know. Force of hinge sounds like a promo for a dating site. Yeah, which we don't want to get into that. But yeah, then we have our downwards forces, which are our two forces of gravity. And these we can actually plug in more directly. Well, I guess let's plug these in generally first to show where they're coming from. This is our FGR and our FGM. And so our normal force, to get it on its own, we just subtract out this Ft sine of 30. And so that's FGR, force of gravity due to the rod, plus the force of gravity due to the mass, minus the force of tension times the angle at which it's being pulled. And this, I don't know if we're going to fit that in that little gap there. I feel a little bad. Our FGR that's 2 kilograms times 9.8 plus 0.5 kilograms times 9.8. I'm just going to omit units now because otherwise we'll never fit this. Minus 29.4 newtons times the sine of 30. Ah, there we go. It's all in the corner there, but we can make that work. So individual terms, we have 2 times 9.8. We have 19.6 plus 4.9. I actually knew that one by offhand. And then we have minus a 14.7. And so, actually then doing these operations gives us a net force, oh, look at that, of 9.8. That's serendipitous. Fn is equal to 9.8 newtons. Cool, cool. Well, any questions on how we set that one up? Well, that was our last one for tonight. So, let me bring this on over here. I want to thank you guys all for coming. We actually had a pretty good turnout. I liked talking in the chat with you guys. I hope you guys learned something about torque and rotational motion. As for next time, we are now done with every individual unit. And next time, we're just going to be doing a cumulative review. That's right, we're going to be going through every single unit, just kind of broadly speaking, but we'll be delving into the main ideas and the different types of equations and relations that we expect each unit to have, what possible test questions might look like, and any other like last-minute questions you guys might have. If you want to find any of our previous streams, you can reach them on either our Twitch channel, our YouTube channel, or they're all now also being hosted on 314education.com. You can also check out 314 Education for more other resources such as online tutoring, or we have a problem blog series, and we hope to get more additions there soon with time. Yes, our next cumulative review, I should mention, it's not on a Thursday. We were going we're going Thursday, Sundays, kind of back and forth. But this time, the test is on Wednesday, so it wouldn't help us to do it on Thursday. We're going to do it on Tuesday. So it's going to be the night before the AP test. So if you're stressing, you're cramming, just kind of jump in the chat. You can hang out with some other students and talk about how you guys are feeling about the test. And then we'll just be going through all the main ideas that you have to be ready for the next day. Follow us on Instagram at 314education.com. Up there. There it is. And thank you for stopping by. Until the next time, you guys take care, keep safe, and I will see you all Tuesday.